Thank you all for standing by. At this time, I would like to inform all participants that your lines will be on a listen-only mode until the question and answer session of the call. At that time, if you would like to ask a question, go ahead and press star 1 to queue up to ask your question. Call is being recorded. If you have any objections, you may disconnect at this time. Please continue to stand by.
Hello, everybody, and welcome to this Telecon, this NASA Telecon about our EMIT mission. This is an instrument on the International Space Station, and we're here today to talk about some unexpected abilities of this mission. I am Karen Fox with the Office of Communications at NASA headquarters in Washington, D.C. We have 4 people on the line today who will be giving brief remarks and then will be available to answer questions. They are Karen St. Germain, who is the Earth Science Division Director here at NASA headquarters. We have Rob Green, who is the EMIT Principal Investigator, Senior Research Scientist at the Jet Propulsion Laboratory in California. We have Andrew Thorpe, a research technologist with the Jet Propulsion Laboratory, and Kirt Costello, who is NASA's Chief Scientist for the International Space Station Program Research Office. We have imagery that you can follow along with. I will say the URL twice, and I'll say it slowly. It is www.jpl.nasa.gov/emit-methane-telecon. So once again, that is www.jpl.nasa.gov/emit-methane-telecon. And with that, I will hand it off to Karen St. Germain.
Great. Thank you, Karen. We are really excited to be here with you today to talk about EMIT. EMIT is one of 25 NASA Earth science missions on orbit today and one of 7 NASA instruments aboard the International Space Station. These missions provide us a global view of our Earth system by observing land, atmosphere, oceans, and ice. EMIT was selected as an Earth Venture mission in 2018, and it's a first-of-its-kind hyperspectral instrument developed at the Jet Propulsion Laboratory. We launched it on July 14th, installed it on the ISS on July 24th, and got what we call first light, or the first data from the instrument, on July 28th. On the screen, you should see an image of EMIT where it is installed on the ISS payload platform. So right now, I should mention that EMIT is offline pending the installation of a replacement power module on the space station, but we expect the mission to come back online and start delivering data again very soon. This is not anything out of the ordinary, and we are really grateful for the support that the ISS provides to keep our instruments going. So EMIT's primary mission is measuring dust sources and the effect of that dust on our climate. But now, EMIT is demonstrating a new and unplanned capability, spotting super-emitters from space. So super-emitters are, they are facilities, equipment, and other infrastructure that emit methane at disproportionately high rates. Methane makes up a fraction of the greenhouse gas emissions from human activities. What's important about methane is it's approximately 80 times more potent at trapping heat in the atmosphere than carbon dioxide, even though it only stays in the atmosphere for about a decade. So reducing methane emissions by identifying these super-emitting sources is regarded as an essential strategy to limiting climate change and one that can really be implemented quickly. And this is especially true if we have capabilities like EMIT where we can identify these sources on a large scale. So NASA has many tools in orbit that are important to measuring changes to our climate, but what makes EMIT special is the new technology and capability, the hyperspectral observations at high spatial resolution and broad area coverage. This unplanned capability of measuring methane super-emitters is super exciting, and along with the other results that we'll see from the EMIT mission, and I'm really eager to see what else EMIT will show us. So with that, I'm going to turn it over to my colleagues from JPL to discuss the findings further. Rob?
Oh, thank you very much, Karen. Again, this is Rob Green. I'm the principal investigator from EMIT. It's a pleasure to be here and share the excitement with these somewhat unexpected results with the first EMIT measurements. I'm going to say a little bit about what EMIT is. The instrument is an imaging spectrometer, and it's designed originally to look at the spectral fingerprints of minerals on the Earth's surface so we can understand how mineral dust is emitted into the atmosphere under conditioned high winds and impacts climate. But in order to see those minerals, we have to measure a wavelength range that includes their molecular signatures. It turns out that methane also has a spectral signature in the same wavelength range, and that's what has allowed us to be sensitive to methane. And just for reference, the signal we're looking at originates from the sun. It's sunlight coming from the sun, passes through the Earth's atmosphere to the surface, is reflected by the surface. That's where we get the mineral signatures, and then back up to EMIT on the ISS, where we measure those signatures with 285 wavelengths from the visible to the infrared portion of the spectrum. And of course, we go through the atmosphere as we try to get those mineral signatures, and that's where we've discovered this signature of methane. So what we've seen are a series of methane super-emitters in a very early data set collected by EMIT just after we returned on. We were doing the early checkout. And I'd like to show you a few examples of some of those detections. I think the first one you'll see on the screen is a large methane plume in the Permian Basin, which is an oil and gas region in New Mexico in the southwestern U.S. And this is a major methane plume. Again, we're seeing the methane molecule in the atmosphere above the surface, and we're able to detect that because it's absorbed energy and left its fingerprints. You'll see the yellow zone in this plume is the high concentration of methane, and then it fades to purple as we get to lower and lower concentrations. So this is about 7 miles long, and we did some initial estimates that this could be releasing methane on the order of 18 metric tons per hour with some uncertainty. So this was, again, a really fascinating large plume that we're seeing in quite nice spatial detail with the capabilities of EMIT. And hopefully people have seen that example on the screen. Now I'd like to move to an even more spectacular example, which we saw quite early in the EMIT data set. And again, we were just checking out the EMIT data, looking at our mineral signatures, looking at the atmosphere, and we started to see these spectacular plumes. So this is from Turkmenistan near the Caspian Sea. And in this single EMIT image, we have 12 separate super-emitters emitting methane into the atmosphere. Again, the scale is the same. Yellow is high methane concentration, fading to purple. Some of these plumes are 20 miles long, and we've seen some longer as well. So this is quite a bit of methane. Again, early estimates, which you'll hear more about from my colleague in a few minutes, are on the order potentially of 50 metric tons of methane per hour. So significant point sources. And we're seeing with a technology that we understand why it works, but it was designed originally to look at mineralogy for our prime science objectives. So that's the second example. Now, the third example is quite interesting as well. This is methane coming from a landfill. It turns out the buried organic waste in landfills, when it decomposes, can be quite a significant source of methane. And this is an area of active research, understanding how much methane is entering our atmosphere from landfills. And this is a significant plume, estimated perhaps at 8 metric tons per hour, coming out of the Earth and into the Earth's atmosphere from a landfill source. So again, this is an area of information that's quite helpful as we understand the different sources of methane as it impacts climate change. So this landfill actually is from the country of Iran. There's no particular reason. It just happened to be where we had collected data and noticed this methane plume. So going forward, as soon as EMIT begins to measure again, we will cover large swaths of the planet Earth, and we'll be looking in places where no one is currently planning to look for methane, but if it's there, we'll see it, and we expect to see it, and report it. So that'll be new information as we all begin to understand the full range of sources of methane entering the Earth's atmosphere and its important role as a greenhouse gas and impacting climate change. So moving on, I will say that all these data will be released into the NASA Land Processes Archive for the public to access and to look at and explore. And in regard to the EMIT instrument, it's quite an extraordinary instrument. It really is first of its kind and class launched into space to date. It has broad area coverage, good spatial resolution so we can see point sources, and excellent sensitivity. That's high signal to noise in our term. And it's equivalent to 1,240 spectrometers collecting 300,000 spectra a second. So it's quite an extraordinary instrument. It's also, I will mention, an important precursor to NASA's surface biology and geology mission that will have more than 6,000 cross-track measurements and is part of NASA's Earth System Observatory going forward. So I'm going to conclude here and pass it off to my colleague, Andrew Thorpe, who is the lead methane scientist working with the EMIT methane measurements here at JPL.
Great, thank you, Rob. So given our previous work using the airborne imaging spectrometer AVERIS Next Generation for methane and carbon dioxide mapping, we did anticipate that EMIT would have sensitivity to these gases from space. And as part of our efforts to check the accuracy of the imaging spectrometer's mineral data, we did in fact verify that EMIT could detect and map methane and carbon dioxide plumes. What we'll be showing next is a figure that shows some of the data products that are generated by EMIT. The left panel will show a data cube from EMIT that covers an area of around 2,500 square miles in Turkmenistan. The methane plumes are overlaid on the image as well, and the rainbow colors that extend beneath the data cube represent the spectral fingerprints for each location within the scene. On the right panel, we show the methane spectral fingerprint as measured by EMIT, as represented by a blue line, and the red line represents the expected spectral fingerprint that was calculated using an atmospheric simulation. And this was a result that we were very excited by, given that there was a near-perfect match between the measured and modeled measurements that we're making with EMIT that emphasizes the high quality of EMIT data. By analyzing each of our methane plumes, we can use the plume shape and the methane concentrations to identify the location of the emission sources on the ground. And we can further attribute methane emissions to specific industry sectors by using higher spatial resolution imagery to resolve locations on the ground and potential infrastructure points that might be emitting methane, for example, emissions from the oil and gas infrastructure or a landfill. The examples that we're showing today are very large methane plumes, both in terms of plume size as well as emission rates. Some of the plumes, like the landfill example, have emission estimates that are within range of other studies that have been published recently. Other studies, like the Turkmenistan plumes, are very large in extent. This example had a plume that was in excess of 20 miles downwind, and the emission rate at 55.6 tons per hour is similar to the Aliso Canyon emission in 2015 from the Southern California Gas Storage Facility. And to put this into context, the Aliso Canyon leak was considered to be the worst accidental discharge of greenhouse gases in U.S. history, so this really underlies the importance and size of this Turkmenistan example. The real strength of EMIT is that it combines coverage of a large portion of the Earth's surface with the spectral and spatial resolution that's required to map methane point sources at the facility scale. And because EMIT is on board the International Space Station, which has an orbit of every 90 minutes, we'll have multiple observations of methane plumes over time, which is really important to better understand if emissions are persistent, that is to say, if we see them over and over, or if the emissions are intermittent. So as we have shown with some of our previous airborne surveys, these types of results are increasingly being used by the public and private sectors, and they often lead to voluntary mitigation. Therefore, we're really excited about EMIT's potential for reducing methane emissions from human activity by pinpointing these emission sources. And to facilitate the sharing of these results, we'll be developing a JPL web portal that will make EMIT methane data publicly available. The results today showcase only a few examples of a limited analysis of EMIT data, and we are really only scratching the surface of EMIT's potential for mapping greenhouse gases. Going forward, I'm really excited to continue looking at different areas and emission sectors to better improve our understanding of greenhouse gas budgets. And with that, I will pass this on to Kirt.
Thank you, Andrew. The International Space Station is a unique laboratory in low Earth orbit. As such, it not only furthers our exploration research for NASA, moving on to the Moon and Mars, but it also has a unique mission of being able to contribute to benefits to humanity here on Earth. The orbit that the ISS takes is unique to some Earth observation typical investigations. They tend to fly in a polar orbit which repeats over the same point at the same time of day, every day. We, however, are in a 52-degree inclined orbit. What that means is that while we orbit the Earth 16 times a day, every time we go over the same spot, you get a slightly different time of day observation. This makes it really beneficial to start to tease out diurnal effects and to be able to see the lighting conditions in various time of day over a particular area. It also means that due to the orbit that we have, we can cover about 90% of the inhabited surface of the Earth, and every 90 days we repeat with the same lighting conditions. So again, a great tool and capability to be able to supply different views to instruments on board the ISS for Earth observation. In fact, we have many different instruments, 7, as you heard earlier, dedicated to Earth science and observations on board the ISS. We have 15 total reconfigurable slots on the ISS for external payloads, and right now, with the addition of EMIT, we are full on those slots. So we are exceedingly happy about being able to contribute to the Earth Sciences Division's interests in low Earth orbit and to be able to supply the type of data that EMIT is bringing to us and talking about today. Lastly, as you heard, there was an RPCM trip, that is a remote power controller module, and since that happened last month, EMIT has been powered down. However, we have a plan to replace that RPCM external to the station on November 10th, and after that time, EMIT should be returned to full operability. So we are looking very forward to those exciting discoveries to come.
All right. Thank you all so much. A reminder that you can gather the images that we've been showing at www.jpl.nasa.gov/emit-methane-telecon. Additionally, we will start taking questions. You can sign up for a question by pressing *1. And we will also, down the road, be taking social media questions as well. You can ask a social media question using the hashtag AskNASA, or if you're following along on YouTube, you can simply drop your question in the chat. So with that, our first question is from Seth Borenstein from the Associated Press. Opening up your line.
Yes, thank you for doing this. I think this one would be for Andrew, unless someone else wants to jump in. Looking at, as you said, the Turkmenistan figures were much higher than expected, and if you could detail how, what was expected and what, as opposed to the 55.6 tons per hour you were getting. but that the Iran landfill was about what was expected. When you look at everything, all the super-emitters you've found so far, and if you could tell us how many of those are you seeing more than was expected, or are you seeing about what was expected? In other words, is this, oh my God, we've got much more methane because methane has been hard to monitor, or is this, yep, this is about as bad as we thought?
I mean, I think we were certainly excited to see the types of examples that we're seeing, and we showcased just 3 examples there. I would say that these are not necessarily unexpected, given the previous work and some of the other studies that have indicated point source emissions from these different sectors, but I would highlight that some are quite spectacular, like the Turkmenistan example, and I did want to highlight that the size and the emission rate relative to Aliso Canyon for sort of comparison. Some of the other examples, like the landfill example, are very large relative to some of our airborne campaigns in California that you might be aware of, California Methane Survey that occurred in 2016 and 2017. But they are not unreasonable based on some more recent publications that have showed emission rates that are that span the range of what we observe, but there are some examples of landfills that are much larger. So we're really excited to continue to look at more data to get a better understanding of the types of emissions globally.
And this, Rob, I might chime in. We didn't know, nobody had indicated that the Permian super-emitter would be there or the landfill super-emitter. We knew Turkmenistan was a place that was worth taking a look at. We happened to get data over it that was clear sky. So while these are in family with other comparable super-emitters, nobody knew to look for these. No one knew of that particular landfill. So the advantage and the contribution we hope we can make is with the broad area coverage, we can see if there are super-emitters in places no one has expected them, much like maybe the case of the landfill. Nobody knew that particular landfill was a super-emitter, for example, maybe to the heart of your question.
So getting just back to it, is it fair to say, I mean, does this change the amount expected from super-emitters, or is this just another good tool to find super-emitters?
I would say that at this point in the early stages, we can't say that it would change the sort of ongoing research area on this topic, but I think these measurements go towards improving our ability to resolve these and look at these populations. And one of the challenges, as you might be aware, is that there aren't enough measurements of these types of emitters, and EMIT will, I think, complement some of the existing sensors that are out there and future sensors to give us more data density where we can start to actually answer the question that you posed, which is a really great one. But unfortunately, at this point, we can't answer it just looking at the select EMIT lines that we have to date.
Okay, thank you.
Great, thank you so much. A reminder to those people on the phone, if you'd like to ask a question, you can press *1. I will go to some questions from social media now. The first question I have is from Mouser58907 on YouTube, who is asking, how long will it take to map all of the Earth that ISS can see?
So this is Rob. I'll take a shot at that. Currently, EMIT's prime mission is to map the arid land regions of planet Earth for our prime mission, which is mineral dust sources. So we can do all of that within 1 year. In fact, we'll have multiple observations because we worry a little bit about clouds. So arid land, there aren't so many clouds. So the areas we're targeting can easily be covered in a year. Then we'll see after the prime mission what the strategies are to expand that coverage. But the area accessible below the ISS is all the land and water, both plus or minus 15 to 52 degrees latitude, as was indicated by Kirt.
Great, thank you. Another repeated question we're sort of getting from social media, a couple people have been asking, is what will be done with these findings? What is the next step after we have located these super-emitters?
This is Andrew. So we are in the early stages of looking at more and more data, as I mentioned before, And what we're doing with that data is we are going to be putting a website together through JPL where we will be visualizing the methane plumes that were observed and making that data available to the public. We are focusing on, we're aiming to have a release in early next year for that. And then, as Rob mentioned, there's also avenues for getting the radiance data that's taken by EMIT and putting it on the LP DAC, which is a NASA DAC that's accessible to any research group that's interested in using the data. And we're certainly aware of a number of organizations that want to look at the data and do their own analyses when it comes to methane point sources as well.
And this is Karen. I'll just augment that answer because NASA is also undertaking a larger effort around greenhouse gases, standing up a new greenhouse gas center, virtual center. So we'll bring the EMIT data into that center as well, and that's a partnership with other government agencies. So these data will begin to inform a broader set of decisions government-wide.
Thank you so much. We now have another question from the phone line. Steve Gorman from Reuters, your phone line is open.
Yeah, hi. So my question is, excuse me. Yep, the question is whether if you could better or go over the comparison of the Aliso Canyon leak in just outside of Los Angeles in terms of size and rate of methane discharge, and how much was to, I think you said you were comparing it to the plumes that you found in Turkmenistan. Did you say that all the plumes together in Turkmenistan, taken together, were on the same order of magnitude as the Aliso Canyon single plume there, or that each of those plumes were like one Aliso Canyon? Maybe you could further describe that. Thank you.
Absolutely. Yep. This is Andrew just responding. So that's a great question, and apologies if it wasn't clear. So we did aggregate the 12 plume examples to have one emission rate that was on the order of the Aliso Canyon blowout in 2015, around 50 tons per hour or so. So not 12 individual plumes, each of an Aliso Canyon scale emission. It's in aggregate for that one scene. Is that more clear now?
Yeah, and what are the sources in Turkmenistan? I guess there's a dozen of them. Maybe they're disparate. They're all different. But is there a typical kind of thing going on? Is there oil and gas operations there, or landfills, or something else that's happening, or do you not know?
Yeah, this is Andrew again. Yeah, we've looked at each of those examples in quite a bit of detail. Some of the plumes are clearly associated with either visible hydrocarbon pipelines at the surface or that are visible in the subsurface. You can sort of see them popping out of the sand. Other emission sources appear to be associated with regions that are nearby that are associated with infrastructure. So these do appear to be consistent with oil and gas infrastructure.
Thank you.
All right. Thank you so much. We will go back to some questions from social media now. Mark Norling on YouTube is asking, how long does it take between collecting the data and making it public? Is that immediate, or does it take months?
So this is Rob. Again, we have a commitment with NASA to get our data public as quickly as feasible, but there's quite a few steps. And right now we're just out of the initial in-orbit checkout phase where we're understanding the quality of our measurements. So our plan right now for the first data sets will be released either late December, early January, fulfilling our commitment with NASA. Once we do that, then future data sets, because we have that processing pipeline now fully understood and working, the new data sets will come out close to the cadence at which we acquire them within a week or so.
Thanks so much, Rob. A reminder that you can ask a question on the line by pressing *1, or if you are on social media, to use the hashtag AskNASA or drop it in the YouTube chat. At the moment, we just have one more social media question, so I will go with that. Mattel Aquarius on YouTube asks, can EMIT detect underwater pipeline leaks, or does the methane get too dissolved or diffused? Maybe we don't know yet.
This is Andrew. We have not tested the capability yet, but I would say that some previous studies using very similar instruments that were developed at JPL have demonstrated that you can, in fact, detect methane plumes over water if you use sun glint. So if you get enough signal from the sun into the instrument, you can do this. We may explore that going forward, but again, we're just in the early stages of looking at the data.
Yeah, I'll chime in. The first detection of methane with an airborne imaging spectrometer was of the methane seeps in the Santa Barbara Channel, and that goes back to about 2010, and that was with an airborne simulator that's somewhat related to the EMIT imaging spectrometer on the ISS.
Thank you both. That was Andrew Thorpe, who answered first, and Rob Green, who chimed in afterwards. Looks like we are finished with our questions for today. So I want to say thank you very much for those of you who attended and for those of you who participated. We will, of course, continue to share information about all of NASA's Earth missions at nasa.gov/Earth. And we look forward to all the things that EMIT is going to do. Thank you all so much.